There's one final matter we want to look at in this chapter, and that is a special type of linear operator called a projection operator. If V is a direct sum of S and T, then the linear operator, which I will denote by rho sub S comma T, this is the Greek letter rho, R-H-O, defined this way for all vectors S in S and T, so that's essentially for all vectors in V, rho S comma T of S plus T is just S. Toss away the capital T component, keep only the capital S component. This is called projection onto S along T. Both of these are critically important when you talk about projection. You must mention both S and T. For a given S, there are lots of complements. You change the complement, you change the T here, you will get a totally different totally different operator. So it's critical to involve both S and T in your statement about projections. Note that projection operator, rho sub st, is well defined if and only if S and T are essentially disjoint. So the projection operator only makes sense when this sum is a direct sum. So whenever we refer to an operator, rho S sub t, st, and call it a projection, we will just assume that you understand that V is a direct sum of S and T. Here's an example. In R3, S is the subspace generated by these two vectors. T is the one-dimensional subspace. It is true that R3 is a direct sum of S and T. To find the projection rho TS, for example, we need to find the unique little s in big S and little t in big T, for which this vector is a sum of S and T. Then we just keep T and throw away S, because this is the projection onto T along S. So, for example, if the vector is 1, 2, 3, we write an equation like this. This is the portion that belongs to capital S. This is the portion that belongs to capital T. Solve the equation. This is a linear system. And then actually determine the two components here, S and T. It's important to emphasize that this double subscript notation is critical. There's no such thing as projection onto S. You have to specify the second component, the complement of S. Just to illustrate, if we use two different complements, we will get two different projections. Even though it's onto the same subspace, it's along different subspaces. Consider this example. Take the matrix space of all n by n matrices over F. This can be written as a direct sum of the upper triangular matrices U and the strictly lower triangular matrices. So these are the lower triangular matrices with zeros on the main diagonal. The projection rho U L naught just erases everything below the main diagonal. But here is another complement of U. It's a funny looking subspace. All these A's are the same entry, and B and C can be different entries. This is a subspace of the matrix space. It is essentially disjoint from the subspace U of upper triangular matrices. You have to check that. And any matrix A can be decomposed into a sum of an upper triangular matrix and one of these matrices in W. So when we project onto S again, onto U, but this time along W, we just get the component that's in U, which is this component. So this is what the projection does as opposed to this projection. Quite a different story, quite different functions. I'll get both these in at the same time. How does that work? Yeah. Okay. Projection onto U along L naught gives this. Projection onto U along W gives this. Eventually we will study something referred to as an orthogonal projection operator. And there we just have the one subspace S, but in reality we have both because it's projection onto S along its orthogonal complement. So the along part is still there, even though because it's uniquely determined by S, we don't need to mention it separately. But that's coming in Chapter 4. Projection operators have a very pleasant property that's not shared by other types of operators. And here is the property. A linear operator tau on a vector space V is idempotent if tau squared equals tau. Or in other words, applying tau twice is the same as applying it once. The second application does nothing. This applies to operators on any vector space, finite or infinite dimensional, this definition. But projection operators do as well. But we're going to eventually be using these in the finite dimensional context. But for now, this applies, unlike this discussion of matrix representations, this applies to arbitrary vector spaces. A linear operator, ρ, on V is a projection operator if and only if it is idempotent. So idempotence actually characterizes the projection operators. As to the proof, if ρ is a projection operator, ρst, then when we apply ρ squared to any sum, s plus t, this, first we apply one ρ to s plus t, we'll get s, and then there carry over the second application of ρ. But ρ of s is s, and that's the same as ρ of s plus t, so ρ squared agrees with ρ on all these sums. In other words, on all of V. Conversely, suppose that ρ is idempotent. We need to find the subspaces S and T for which ρ is projection onto S along T. And those are going to be the image and the kernel. Because ρ is idempotent, these two are essentially disjoint. because if V is a vector in common to the two subspaces, then because it's in the image of rho, it's a row of x for some other vector x. And so 0 is row of V, because V is in the kernel of rho, and that is rho squared of x, which is row of x, because rho is idempotent, and that's V, so V is 0. So these two subspaces are essentially disjoint. Moreover, if we take any vector little v in V, we can decompose it into this sum. This is in the kernel of rho, this is in the image of rho. So V is in fact a direct sum of the kernel of rho and the image of rho. This only works because rho is a linear operator, so that the kernel and the image belong, both of them belong to V, or subspaces of V, and because rho is idempotent. Otherwise, these would not be essentially disjoint. Finally, to see that rho is actually projection onto the image of rho along the kernel, suppose, again, we write a little vector, a vector V as s plus t, where s is in the image of rho, so it's a row of x, and t is in the kernel of rho. Then, of course, rho of t is 0, so rho of s is row of rho x, rho squared of x, which is row of x, because rho is idempotent, and that's equal to s. So rho maps s to itself. Any vector in image is mapped to itself, and any vector in the kernel is mapped to 0. So rho of s plus t will just be mapped to rho of s, or s. So rho is projection. Finally, here are some basic properties of projection operators whose proof I leave to you. If V is the direct sum of s and t, then if we add the two projection operators, projection along s, onto s along t, and projection onto t along s, we just get the identity. Again, if S is the direct sum, if V is the direct sum of S and T, the kernel and image of the projection operator, rho ST, the kernel's T, the image is S. So V is actually being decomposed here into the direct sum of the image of the projection and the kernel of the projection. And so vector V is in the image of the projection operator if and only if it is not moved by that operator. Finally, if sigma is any linear operator with the property that V can be decomposed into a direct sum of the kernel and image of the operator, and if when we restrict to the image we just get the identity, this is the idempotence part, then sigma is in fact projection onto the image along the kernel. Okay, so I suggest that you spend some time trying to prove these results and then not worry about it too much. It's going to be a while before we get back to these kinds of projections. I wanted to introduce projection operators to you so that when we get back to them later, you will at least have them somewhere in the back of your mind. It's better to be introduced to something, say, more than once. So we'll reintroduce these later on. But I want to end with a general note here. We started this lecture with invariant subspaces, which are critically important, as we've seen, especially reductions of an operator, but even individual invariant subspaces can form the first step in finding relatively simple matrix representations for operators. And as I have said, this is one of the most important issues in elementary linear algebra. It will occupy our time considerably later in the sequence. How to best represent a linear operator by matrices. What ordered basis to pick to get a relatively simple, as simple as we can, matrix representation for the operator to expose as much of the operator's structure as possible. Greetings, this is Professor Roman, and we are going to continue our lectures on linear algebra. We come now to a topic that is going to be very important to us in our future study of linear transformations, in particular linear operators. And that is the notion of an invariant subspace and a related notion of a reduction of a linear operator. Speaking in general terms, how does one study the structure of a complicated mathematical object, such as a linear operator? Well, one answer is to try to decompose that object into simpler objects. This is a theme that exists throughout mathematics. The problem is that if the simpler objects that make up the original object don't have any independence from each other, then problems can arise. The goal is to take a mathematical object and to decompose it into simpler objects that can be studied on their own merit, independently of the other parts of the original object. Just as an analogy that's maybe not too good, think about an automobile engine. It has a fuel system, fuel injection, gas tank, fuel lines, all that, the components that make up the fuel system. It also has a steering system. If you wanted to study those two systems separately, it would be best if they were independent of each other. If how the fuel injection worked depended on how the steering worked, you couldn't separate the two and study each component separately. So we're looking for a certain amount of mathematical independence when we decompose a mathematical object. And I'm not speaking about linear independence or dependence. I'm speaking in more general terms, as you'll see when we get to more details. We have already seen decomposition in action with respect to vector spaces, and it's called the direct sum. So if V is the direct sum of S and T, then we've decomposed V into the sum of two subspaces, which, if this is a non-trivial decomposition, at least the subspaces have smaller dimension than V, so that makes them in some sense simpler. It is in fact the essential disjointness in a direct sum that gives these simpler pieces their independence. So that's the sense in which we mean independent in this context. So S is a vector space in its own right, so is T. They can be studied independently of each other. Whatever structure we discover about S and about T will reflect in the structure on V. Now, we can attempt to use a direct sum decomposition of the domain of a linear operator to decompose the operator. And we do that simply by restricting the operator to each of the subspaces or to each of the direct summands. And this would work for direct sums containing more than two summands. But there is a potential problem. Each of these objects needs to be studied on its own right, and so we're going to need some independence in order to do that. We don't even know if these are legitimate linear operators. Is the restriction of tau to S actually a linear operator on S? If what we do know is that when we restrict tau to S, it maps S to V. The same thing for tau. Restricted to T, it maps T to V. So these are still not quite independent because they have the same codomain, and so their images may in fact overlap. That we do not want. In order to guarantee that, say, the restriction of tau to S is a linear operator on S, it must be the case that for every vector in S, its image is also in S, not just in V. Or put more succinctly, tau of capital S is contained in capital S. So if this holds, and if it holds also for capital T, tau of capital T is contained in capital T, now we have two linear operators on two subspaces that are, well, independent, you might say, essentially disjoint, and we've really decomposed tau into two separate independent pieces. And the domains of the two pieces are smaller than the original domain, again, assuming this is a non-trivial decomposition, so we've made some progress. First, this calls for a definition. Let tau be a linear operator on V. A subspace S of V is said to be invariant under tau, or tau invariant, if tau of S is contained in S. Or put another way, if tau restricted to S is a linear operator on S. And we'll also say that tau admits the invariant subspace S. Now, comes a somewhat subtle point. When we restrict tau to S, we get a map that looks like tau restricted to S maps S to V. Even if S is invariant, so the image of this map is contained in S, technically the restriction of a function just restricts the domain. We also want to restrict the codomain so that when we refer to the restriction of tau to S, we are restricting both the domain and the codomain. That works if and only if S is tau invariant. So here's the convention we will adhere to. Unless specified to the contrary, whenever we refer to the restriction, tau restricted to S, of a linear operator tau to a tau invariant subspace S, we are referring not to the linear transformation from S to V, but to the linear operator from S to S, on S. Thus, we are restricting both the domain and the codomain of the original operator in order to obtain a linear operator. It's possible that most authors do this or intend to do this without clear explanation, so I don't think this is a radical idea. And you will see later that it is very useful. It's pretty clear that every linear operator admits at least two invariant subspaces. The trivial subspace is invariant because 0 is sent to 0, and the whole space is obviously invariant. Of course, those two invariant subspaces are of little value. Here's a couple of examples. F sub m square bracket x, this is the subspace of the polynomial space consisting of the polynomials of degree m or less. This subspace is invariant under the derivative operator, because if we take the derivative of a polynomial of degree m or less, the result is a polynomial of degree m or less. So D maps this subspace into itself. It does not map the subspace onto itself, because you can't get, say, x to the m by differentiating a polynomial of degree m or less. So this is actually a proper inclusion. On the other hand, this subspace is not invariant under multiplication by x. Because obviously, if you take x to the m, you multiply by x, that's no longer in this subspace. Another example, the subspace of sequences with finite support over F. This is a subspace of the sequence space, full sequence space. This is invariant under both shift operators, left shift and right shift. But the subspace S of the sequence space, consisting of all sequences whose first term is 0, that is a subspace, is invariant under the right shift operator, but not under the left shift operator. So when we restrict the left shift operator to this sequence space of sequences of finite support, we get a map from this vector space to this one, but it's not a linear operator on this vector space. The existence of a non-trivial, proper, invariant subspace S of a vector space V is very helpful as a first step in finding a relatively simple matrix representation for the operator. Okay. And this is the reason right here. Remember that one of the major goals of this course is the study of matrix representations of linear operators and the problem of finding as simple a representation as we possibly can. A representation, a snapshot, that reveals as much of the structure of the operator as we can. So this is the doorway, you might say, to that problem. And it is the existence of invariant subspaces for the operator. V is finite dimensional vector space. We're talking about matrix representation, so that means we're talking about finite dimensional linear operators. Tau is an operator on V, and S is a tau invariant subspace. Now, if we take a basis B, an ordered basis, for S, we can extend it to an ordered basis C for V. Then the matrix representation of tau with respect to C has this block form. Maybe I should draw lines here, I don't know, just to emphasize the blocks. This is a good first step in finding a relatively simple, and I emphasize the word relative, as you will see later in the course, relatively simple matrix representation for the operator. In the upper left block, we have the matrix representation of the restricted operator, restricted to the invariant subspace. Here is why we need to restrict both the domain and the codomain. If we didn't restrict the codomain, all these zeros below would have to be included in this matrix representation. So we wouldn't get this four-block form here. Up in the upper right block, we have no idea what's going on. We have no control over it. There's nothing we can do with it really, so I just put an asterisk. The lower right block, we also don't know what it is, but I refer to it by letter because we're going to do some things with it. Unfortunately, much later, we have a lot of ground to cover before we're ready to start tinkering with R. But the idea basically is that we want to repeat what we've done here for R and break this submatrix R into a 2x2 block form and keep doing that. But that's quite a bit in the future, so I won't go into that any further right now. But this is the first step in finding a nice, relatively simple matrix representation for a linear operator. The proof here is pretty straightforward. Let's say here's our basis B for the invariant subspace S. Then the invariance of S implies that the image of each of these basis vectors is a linear combination only of these basis vectors. They don't involve any other vectors from the full basis C. And so when we create these first M columns of the matrix representation, they're going to look like this. You're going to have the coefficients in this linear combination, then you're going to have all zeros. These are, if you wish, the coefficients in the representation of tau UK of the other basis vectors in C. They're not in B, so that's why these are all zero. And then we don't know, again, what's going on here. So we end up with this matrix. As a special case, note that if tau should happen to admit a one-dimensional invariant subspace, so that would look like this, the space spanned by a single non-zero vector. So tau of v is a multiple of v. Then we can use this, the set B as a basis. Maybe I'll even put that in here. And we extend it to an order basis C for capital V. And this is what the matrix representation looks like. It's the same as this, but we up here in the upper left block, we have a 1 by 1, just lambda. So here we're getting really serious. The first column of this matrix representation could not be any simpler. It's got a single entry, which may be 0 or non-zero, and below it are all zeros. You may recognize this, something we're going to study in Chapter 4, and that is lambda is an eigenvalue for tau, and v is an eigenvector. So the presence of eigenvectors gives us a very nice start towards finding relatively simple matrix representations. If V is a direct sum of S and T, the fact that S might be tau invariant does not imply that T has to be tau invariant. And I will leave that for you to think about. There's a simple example you can produce even for V equals R2. So this prompts another definition. And here's a picture to support that. Vector space V is a direct sum of S1 through Sm. If each direct summand is invariant under tau, then the restrictions, each of the restrictions, say just take the restriction of tau to S1, is a linear operator on S1. Same thing for the other restrictions. We have decomposed tau into a number of hopefully simpler, independent linear operators. When that happens, we refer to this direct sum as a tau invariant direct sum. It's a direct sum for which each summand is tau invariant. And we will permit ourselves to use the direct sum notation for these restricted operators. We've already defined the sum of linear operators, so we are now defining the direct sum. We also say that the original direct sum here reduces the operator tau, or is a reduction of the operator tau, provides a reduction. I guess I should actually say the direct sum reduces tau, and that this is a reduction. So I'm going to change that just a little bit. Okay, so if this direct sum is tau invariant, if each of the subspaces is tau invariant, we say that this direct sum of the domain of tau reduces tau. And we'll say that this reduction, well, I just said it. We'll say that this sum is a reduction of tau. A non-trivial reduction of a linear operator is the ideal situation for studying the operator because it decomposes the operator into independent and hopefully simpler operators. At least they're simpler in the sense that they're on smaller dimensional vector spaces. Specifically, if we take an ordered basis B sub I for each invariant subspace S sub I, then this ordered union is an ordered basis for V, and the matrix of tau with respect to this basis looks like this. It's block diagonal. Now this form is very general. If there was only one block, I wouldn't have achieved anything. But we will be able to set this up so that each of these blocks, in restricted context, each of these blocks has size 1 by 1 or 2 by 2. So we have indeed made a simplification. There are multiple blocks. This could be this size n by n, or n could be any number, and yet these blocks are all size 1 by 1 or 2 by 2. We have achieved a significant simplification in our snapshot of tau. We may have to back off on this by allowing this block, these zeros appear to be arbitrary elements, keeping the zeros down here. So we've still got what might be considered a relatively simple matrix representation. But all that is unfortunately going to be a bit in the future. So we'll have to hold those thoughts for a while. Here's an example. This is a linear operator on R5. I just constructed this as an example. It has no particular meaning, but the subspace consisting spanned by the first two standard basis vectors S1 and of the last three basis vectors are both tau invariant, and their direct sum is R5. So this is a tau invariant decomposition, tau invariant direct sum. Therefore, each of the restrictions is a linear operator on the respective subspaces, and the matrix representations look like this. So to get the matrix representation of tau with respect to the full standard basis, we just stick those in these two matrices in diagonal blocks in either order. And so you can see from this that we have achieved at least some semblance of simplicity. What does it mean to say we have a simple matrix representation? Well, there are some obvious cases. If the matrix is diagonal, that's pretty simple. If it's upper triangular, it's better than nothing, and quite a bit better than nothing. This doesn't qualify to be either of those, but at least there are a lot of zeros. And the more zeros, in some sense, the simpler, provided the zeros are not just randomly scattered. I mean, even if they are, that's, I guess, better than nothing. But when they're grouped in blocks like this, we are getting a simple, we're getting reasonably simple matrix representations.